In this research, I investigated a property of Fibonacci sequence involving matrix determinant. The Fibonacci sequence was published by Leonardo Bonacci in his book Liberace. Each successive term in the sequence is recursively defined as the sum of the preceding two terms starting from 1 and 1. In this project, we generated the first 7,000 terms of the sequence using Java. We then used SageMath to extensively investigate the properties of the sequence numerically. With the help of some well-known properties, we established a new property which involves the determinant of a matrix containing terms of the Fibonacci sequence. The three well-known properties which we studied are Cassini's identity, D'Occagni's identity, and Kaitlyn's identity. Using Microsoft Excel, we were able to manually study numerical data from matrices of these types. Through the study of this data, we were able to identify a pattern and validate it using SageMath for the first 7,000 terms of the Fibonacci sequence. Let us define a new matrix, ARS, as follows. ARS is equal to the determinant of this matrix of Fibonacci numbers. From here, we have two results. Theorem 1, let R and S be in the set of natural numbers with R greater than or equal to 2 and S greater than or equal to 2. If ASR is equal to ARS, then R and S have the same parity. Theorem 2, let R and S be in the set of natural numbers with R greater than or equal to 2 and S greater than or equal to 2. If R and S have the same parity, then ASR is equal to ARS. We first proved Theorem 1 using the contrapositive of the statement. Let ASR equal to ARS. Suppose R and S do not have the same parity. Let R be even and S be odd. Then ASR is equal to the determinant of this matrix. Using Kaitlyn's identity, ASR is equal to this value. Thus, through simplification, ASR is equal to this. Similarly, for ARS, we have ARS is equal to this value. And since ASR is equal to ARS, then these two values are equal, which implies F2n plus 1 is equal to 0. This is a contradiction because no F number is equal to 0. Therefore, if ASR is equal to ARS, then R and S have the same parity. Proof of Theorem 2. We prove this through direct proof. Case 1. R and S are both even. R is 2m and S is 2n for some m and n in the set of natural numbers. Then, ASR is equal to the determinant of this matrix, and by Kaitlyn's identity, ASR is equal to this value. Therefore, ASR is equal to this, and similarly for ARS, we have ARS is equal to this. As you can see, these two values are equal to one another. Therefore, ASR is equal to ARS. Case 2. R and S are both odd. Let R be equal to 2m plus 1 and S be equal to 2n plus 1 for some m and n in the set of natural numbers. Then, ASR is equal to the determinant of this matrix. By Kaitlyn's identity, ASR is equal to this value. Thus, through simplification, ASR is equal to this. And similarly for ARS, we got ASR is equal to this. Therefore, these two values are equal, and ASR is equal to ARS. Before proving this formally, we verified this numerically using SageMath. Here is the following snippet of code that we used to show that there are no R and S of the same parity when ASR is not equal to ARS, and also there are no R and S of the opposite parity when ASR is equal to ARS. Here is a numerical example. Because we have proven this for all values in the Fibonacci sequence, we can take R equal to 102 and S equal to 506. These two numbers have the same parity. Therefore, this determinant is equal to this determinant. These two matrices are of the form ARS and ASR. In this project, we established that ASR is equal to ARS if and only if R and S have the same parity for R greater than or equal to 2 and S greater than or equal to 2. Future work for this project includes investigating more properties of similar nature for the Fibonacci sequence.